This is going to be section 5. Section 5. You can have this back. Should I put it in here? That's not working.
Pass those down. Pass them down.
Okay. Section 5. Cool. It's cool. You got bra here. Volumes of gases combine in whole numbers. That's the law of combined volumes. Volumes of gases combine in whole numbers. So for example, let's say we have N2 gas, H2 gas goes to NH3, and we bounce this a 1, a 3, and a 2. So over there we've got it all balanced. That 1 and 3 and 2 mean a couple different things. Right, Big Porter? It could mean molecules. So 1 molecule of N2 goes to 3 molecules of H2 and produce 2 molecules of NH3. It could mean also moles. So we've seen both of these two. 1 mole of N2 goes to 3 moles of H2 and produce 2 moles of NH3.
Whose side are you on?
It could also be volume. So 1 liter of N2 goes to 3 liters of H2 and producing 2 liters of NH3. And this conversion is made by that 22.4 liters per mole. Okay? All right. And so this is called the law of combining volumes. This leads us to a new molar express. A little weird. A little loose. Okay. So, to go between volume and moles, really there's 3 ways now. You can use the ideal gas law to go between volume and moles. You can use 22.4 liters per mole, or that capital M. What does capital M stand for? Molarity. That's an old thing from chapter 4. You go, if it's a liquid, you use molarity. If not, you can use, if it's a gas, you can use the ideal gas law or that conversion. The law of combined volumes adds another pathway on the very top called that volume ratio. Whoa. They're planking. They're planking. Wow. I've only seen that on Google. So, we can go using the law of combining volumes. We can go between volume to volume using the volume ratio. So let's try a little example. Using the same formula from before, let's say we had 5.55 liters of N2, and I wanted to know the volume of NH3. Well, how would I get there? Now that I know my volume ratio, I can use the volume ratio to get one. They're still plinking. That is cool. I'm glad to see it in person. Okay. You haven't seen it before, Google Images. Get your iPhone out. Okay, so we want to know the volume. So 5.55 liters. Now we can use the volume ratio, and we can say, well, there's 1 liter of N2 for every 2 liters of NH3. And that we can go straight to now the volume of NH3, which in this case we calculate out to be 11.1 liters of NH3. And these are all gases, so we can do this calculation.
Gases.
So we can do that. So we can do this calculation to get 11.1 liters of NH3. If we didn't use the volume ratio, we'd have to convert the initial volume to moles, do a molar ratio, and then convert the final moles to volume. So it'd be a much more. Oh my gosh. Are you owling right now? Okay. Let's see. Section 6. Okay, section 6 is called mixtures of gases. Mixtures. Oh my gosh, it's the reverse plate. Wow. That's impressive. That's impressive. Okay, that's nothing. That's nothing. All right. Mixtures of gases. And in mixtures of gases, we're going to learn something, another law for gases called Dalton's law. Dalton's law, and it could also be called the law of partial pressures. Some people don't have a space bubble. They just get a little awkward. That's okay. I don't have one of those. Okay. And it says this. Sometimes I spit when I talk. So let's say, for example, you have more than one gas in a mixture. Say you have gas A, gas B, gas C, etc. If you add the pressures of those individual gases, they will equal the total gas of the container. And that's called Dalton's law, or the law of partial pressures, or Dalton's law of partial pressures. Any one of those for a mixture of any said gases. In this case, gas A, B, C, whatever. You can also say it works for the moles. And this one, hopefully, is kind of somewhat intuitive after the last couple chapters. If I add the moles of, say, gas A, gas B, gas C, whatever gases I have, they're going to sum up to the total moles. And this also fits under the umbrella under Dalton's law that sometimes we'll need to add up the moles to get the total moles. The total, and hopefully this is also somewhat intuitive, equals, say if we have gas A, B, C again, etc., all mixed up together. If I know the volume of gas A, the volume of gas B, the volume of gas C, I can add them up for total. Yes, that cute lady right here. What's up? Sorry, I had to release some stuff. Does this only work at standard temperature? No. So the conversions that you saw before, the 22.4 liters per mole, that does. Now these are only true for ideal gases. So we're always assuming ideal gas, high temperature, low pressure. High temperature is like room temperature or higher, anywhere in that range, or 0 degrees Celsius and higher, somewhere around there. A low pressure would be around atmospheric pressure, somewhere around there. Okay, and if that's true, hey! If that's, what are you drawing?